Hello to AP Physics. I'm sorry that we had another snow day, but I wouldn't want you to be left behind with nothing to do. So we're going to move ahead a little bit with our next unit, which has to do with circular motion. And it turns out that when circular motion can involve two different kinds of motion. It could be a rotation, and that's when the entire object moves in a circle. So a tape can do that. A bicycle wheel can rotate. We can take a water bottle and simply spin it, so to speak, and it rotates. But you can also look at individual pieces, as in the edge of the tape, which doesn't rotate, but it simply revolves around. And the idea is rotation involves a point in here that you're making motion around. So once again, the entire bicycle wheel can rotate, but an individual piece on the bicycle wheel does not rotate, it revolves. And so the difference is the axis inside you or is the axis outside you. And those are the two different kinds of circular motions we're going to deal with. It would help if you had some experience with the unit circle, but you don't have to. In a unit circle, we do talk about motions this way, which they call positive, and motions this way, which they call negative for whatever reason. That is similar to most of our number lines, which have positive on one side and negative on the other. It's just a convention that you have to get used to, and it's not that big a deal. Well, there's other things we can measure in turn, and the biggest thing we're going to measure to start with is the angle that you cut out. And most of you are used to things like, let's say, a 90-degree angle or a 180-degree angle. But if we're talking more than one circle, we can measure rotations or revolutions. So as an example, if I go around the circle once, that's one rotation or one revolution. And most of you already know that that's 360 degrees. But there are other measurements. We can also measure our angles in radians. And for those of you, again, that are used to the unit circle, we know that all the way around the circle one time is equal to 2 pi radians. That's just what they decided on. So one circle is 2 pi radians. One circle is 360 degrees. One circle is one rotation or one revolution. And there's actually another system out there which actually makes more sense to me than any other system called gradients, where a full circle is 400. And that number actually is much easier than any other number, because that a quarter of a circle is simply 100, a half a circle is simply 200. Unfortunately, probably engineers are the only ones that use that, but I wanted you to have seen it once. Well, we're going to do more than just one circle at a time. So we're going to have to be able to go maybe 2 or 3 circles. So as an example, if we went in 3 circles or 3 revolutions, well, we would simply take 360 times 3, we know how to do that. We would take, again, one circle is worth 2 pi radians. It's just a different measurement. But if you went through 3 circles, well, then you would have done that 2 pi, another 2 pi is 4 pi, and another 2 pi would take you to 6 pi radians. And of course, this is actually the easiest one, because if a circle is 400 gradients, then if you multiply that by 3, you're going to be at 1200 gradients. We can also do partial circles, obviously. In fact, what if we only went through, let's say, 3/4 of a circle? That's only 3/4 of a rotation or revolution, and most of us know that that would be 90 plus another 90 plus another 90 is 270 degrees. Radians, well, we're going to have to think, okay, 3/4 of a circle. If a full circle is worth 2 pi radians, then 3/4 of a circle is simply equal to 3/4 times 2 pi radians. And those of you that are used to unit circle recognize that's the same thing as 3 pi over 2, or 3 over 2 pi if you do some simplification. Of course, here that would just be equal to 100 plus 100 plus 100 is 300 gradients. So we can measure full circles, we can measure partial circles, but get used to, most of the time, these are the two that we're going to use, are degrees and radians. And once again, 360 degrees is the same thing as 2 pi radians. So even though gradients are fun and easy, we're not going to use them most of the time. We are going to use this symbol, theta, to represent the angle, and theta can be measured in degrees or radians or any of those other measurements, but we're going to get used to that and measuring the angle that we've cut out. The other thing that we can measure pretty easily is how far you've walked, and there is a difference between the angle that you cut out, as in 90 degrees, and how far you physically had to walk to get there, because obviously the size of the circle will change how far you've walked. In either one of these circles, from here to here, I've cut out a 90-degree angle, but I think most of you would understand that you had to walk further on the outside of a bigger circle than you do in a smaller circle. And not surprisingly, we have something to measure that, and our position letter has been X, and it's going to continue to be X. So now X doesn't measure how far linearly, but it still measures how far you walked around from where you started. It's still measured in meters. And there's got to be a relationship between these two, okay, if you think about it. So if we go through only part of a circle, then we haven't walked very far. If we go through even more of a circle, you've walked further. So these are directly proportional to each other, okay? And the easiest example we're ever going to have, again, let's go back to the unit circle. And when I say unit circle, that means a circle that's centered at 0, 0, and it has a radius of 1. So we know that the radius from the center to the edge is 1. Well, if you walk around all the way around that circle, we know that the angle that you've carved out is 2 pi radians. We're going to do everything in radians for a while, so get used to that. By the way, they don't usually write it out. It looks like 2 pi rad. We still say 2 pi radians. Question would be, that's the angle. You've gone through 360 degrees or 2 pi radians, but how far physically have you walked? Well, most people will recognize that that's the same thing as asking for the circumference of the circle. So in this particular case, how far you walked is the circumference of the circle. And if you take a minute to remember that the formula for the circumference of a circle is 2 pi r, and in the unit circle the radius is 1, it turns out, for good or for bad, that the angle that I've carved out and the distance I physically walked are the same number, which confuses people because one's an angle and one's a physical distance. They're not the same thing. So it's probably more instructive maybe to look at a different size circle. So let's not look at the unit circle. Let's look at a bigger circle, maybe something that has a radius of 3. So from the center out to the edge, it's a radius of 3. Well, if I walk all the way around outside the circle, I've still covered 2 pi radians. That didn't change. But now the distance I walk, because it's a physically bigger circle, you're going to go through the same process and recognize that how far you walk, that's still the circumference of the circle. But now it's 2 times pi times 3, which if you simplify it obviously, is 6 pi, and this is measured in meters. Now we recognize that these two are not the same number. They how in fact are off by a factor of 3, which is the radius of the circle. And we could go through some more examples if we wanted to. If we only went through, let's say, 3/4 of a circle, well, we could do the same kind of thing. If you only go through 3/4 of a circle, that's not 2 pi radians anymore. If 2 pi radians is a full circle, then each quarter of a circle has to be pi over 2 radians. And pi over 2 plus another pi over 2 plus another pi over 2, that gets you to 3/2 or 3 pi over 2 radians. Well, how far have you walked? If it's still a circle of radius 3, we would take 2 times pi times 3, but that would be for an entire circle. And we did not walk an entire circle, we walked 3/4 of that, and most of us would recognize, therefore, that you need to take 3/4 of that number. Well, if you do a little bit of simplification, you're going to find out that the 2 pi times 3/4 is 3 pi over 2, so that this circumference, or how far you walked, it's not a circumference anymore because we didn't go all the way around, but the distance you walked is nothing more than 3 over pi 2 times 3. What we're going to recognize at some point, and we've done through 3 examples now, if you look at the angle and how far you have walked, they're always off by a factor of exactly the radius of the circle. And so we have an equation that says this is not this, but in fact is off exactly by a factor of r. Once you look at this equation a little bit, it makes some sense because it says how far I have to walk. Well, that depends on what portion of the circle or circles I've traversed, but it also depends on how big the circle is. And the bigger the circle is, the further I have to walk. So that equation is in your book. That equation I do not believe is not on your formula page. It's something we have to get used to. But think about it and go and just ask yourself, look, what does this depend on? And this depends on the angle that I've carved out, and it depends on the size of the circle. And that equation goes pretty well. Other things that we can measure besides x, we have also measured v. In fact, we know the slope of the position graph is a velocity. Well, this is simply measured in meters. This is measured in meters per second like we're used to. This measures how much ground I've covered per second. Well, in a circle you can do similar things. You can ask yourself how many degrees per second. As in, if I went in a full circle which would be 360 degrees. And if it took me, let's say, 10 seconds to do so, I would simply take 360 divided by 10. I would take the angle divided by how long it took. So I can measure meters per second, but I can also measure angles per second. And I know we're still used to degrees, but we're going to have to shift. We're going to have to shift to radians. So if I did go through a full circle, which is 2 pi radians, and it took me 10 seconds to do so, whatever this number is, my answer is in radians per second. Now we're not asking how far you're running, we're simply asking at what rate are you spinning in a circle or rotating or revolving, depending on what you're doing. It's not a big step to make to recognize that there's got to be a relationship between how far you are or how fast you are actually running and how far the circle is spinning or how fast the circle is spinning. So if I do something like this, if I spin faster, then someone has to run faster to keep up. And it's not a big surprise that these things share a very, very similar relationship to the distances. In fact, they are exactly off by a factor of r. Now I just introduced a new symbol to you. That is omega. That's exactly what we measure when we measure radians per second. So how fast you're going linearly, that's called velocity, you're used to that. This is a new, it's a lowercase omega, but it's measured in radians per second. Again, it simply measures how often are you spinning around versus how fast you have to run to keep up with that spin. We've also measured something else in the past many times. We have measured acceleration. And you can accelerate by going faster and faster and faster and faster, or slower, slower, slower. But you can also accelerate in a circle. And you could start out swinging around very slowly and then start doing it faster and faster and faster. And you would be accelerating in a circle. Well, the counterpart to acceleration is the Greek letter alpha, which they're both A's. This is measured in meters per second like you're used to. This, however, is going to be measured not in meters per second. It could be degrees per second. It could be rotations per second. But not surprisingly, we're going to measure it in radians per second. So that simply measures how much am I speeding up. If I start out slowly and then start spinning faster and faster and faster, I am accelerating in a circle, and we're going to use those units to go with it. It's not a big surprise, since these two things that we are very used to are off of our counterparts by a factor of r, as is this. So the relationship is not a big surprise that the thing we already know, which is acceleration, equals the thing that we don't know, or the thing we're not used to, I should say, offset by a factor of r. So it's not a big deal. You're probably going to have to memorize those, but they're very common sense, and they're all similar, and that helps a bunch. One last thing that we're going to need to be able to work with, and I'll get rid of this for a second, perhaps our favorite equation, or one we've used many times, is our position equation, which says x equals 1/2 times a times t squared plus the beginning velocity in the x direction times t plus our beginning position. Well, there's a counterpart. If you want to know not how far you've walked, but just how many radians you have spun through, let's say, well, we call that theta, and this is the counterpart. You keep going. The counterpart to acceleration, we know, linear acceleration, is the angular acceleration. T is just t, so that doesn't change any. Our beginning running rate, well, the counterpart to that is our beginning spin rate, again, omega 0, and I'm not going to put it in the x direction, so times t, plus, well, our normal beginning position, but now our normal beginning position isn't meters, it's, well, where did you start in the circle angle-wise, and so it's not a big surprise that that equation turns out to be what it is. Once again, I don't believe that those equations are on your formula page, and if they are, good for us. So it's just about making analogy. So everything you know about linear motion, just try to change it and make it into circular motion, and you're going to be just fine. In fact, if we go to maybe what actually is our favorite equation, the other one, the equation Galileo would have wanted, which is v squared equals v0 squared plus 2 times a times x. The counterparts fit in just as well. The counterpart to linear velocity is angular velocity, it's still squared. The counterpart to beginning velocity in the x direction is beginning spin rate, plus the counterpart to linear acceleration is simply alpha. and the counterpart to linear motion is how much the angle you swung through, and that is theta. It's going to take a little bit of practice to get used to those, but I think if you do so, you're going to become pretty comfortable. Once again, those of you that are comfortable with unit circle come faster, but in the past we've never had people that couldn't get it. It just took a little bit more time. So, for good or for bad, I have given you an introduction into circular motion as the bell rings. That was fun. What I need you to do is to get started on this. We cannot simply afford another day off. So, I need you to take a look at the beginnings of chapter 7, and in the problems, not the concepts, I need you to complete 1, 3, 5, 6, 7, 9, 10, 12, 18, and 20. Give me your best effort at those. I'd like them done for Monday. On Monday, even though we're taking a test, I'm going to look to see that you've at least started that. And then definitely by Tuesday, that needs to be done so that we can keep moving. Thanks for your time. Enjoy your snow day, minus maybe 45 minutes of work or so, and I hope you have a good weekend.